All right. Hello, those who are watching on video. I've already said hello to everyone who's here at the moment. I hope the future is better. Those who are watching in the future, and this is a revision seminar from semester 1, 2022 for Differential Equations II. Our requests are pretty light on the ground, and I think we need some inspiration. I mean, well, few people have some questions and we'll get to those too. But we're going to start off with a bit of a brainstorm of stuff that's in this course. So, what's in this course? Yep. Cool. So just to slow that down a bit, that's a series method of solving differential equations. And method of Frobenius is a specific one of those. Is that right? Am I interpreting that correctly? Okay, cool. What else? Did we just check? Oh, yeah. Oh, wow. Oh, stop, I'm going to write some things down. So just saying one-dimensional autonomous. Okay, and then you've got Fourier series. How long did we spend looking at PDEs? And that's the last thing you've done? Yep. I remember that assignment. Yes, yes, there was a big PDEs assignment. Cool. And the Fourier series linked in with the PDEs. Like when you did the PDEs, you had to notice like you get infinite sums of causes and or sines when you do that. So they link together, those things. Okay, cool. All right. With our second order ODEs, anything more specific there? Names of methods? Not sure what that means. I'll get back to that. So yeah. All right, cool. This is a good thing to be able to do. So, I have been asked to talk about, I mean, there's other things. I mean, it took 12 weeks to do it. I'm sure we can't cover every terminology in, what, 3 minutes. But if something comes up, then feel free to add it to your own brainstorm or say, oh, I thought of something, David, and I really like to talk about it. That's fine too. Okay. So the beginning of this course builds on assuming that you've seen the stuff that was in Maths 1B, but it sort of doesn't really assume that, but it needs to because it does it really quickly, the first order stuff. Did you go over again the integrating factor? And you went over second order linear ODEs with constant coefficients. Yep. Okay, cool. Right. All right. So the first question that was put on the board concerned second order linear ODEs with constant coefficients. And so that's, oh, actually, I've thought of one thing. Did you do systems of ODEs in this course? but they were like eigen things. Yeah, okay. Cool. All right. Constant coefficient linear ODEs. So this is something that was in Maths 1B. You extended it a little at the beginning of DEs 2, and then you used it when you were doing PDEs later. And so it's really important to have a good handle on how it works and an efficient handle on how it works so that you can do it quickly enough during an exam, because you're going to have to do it when you're solving PDEs. And I do not get to see the exams. I barely even get to talk to the lecturer. I have no idea what's in the course, but what's in the course exam. But considering how much effort we spent being assessed on it during the assignments, I reckon it's probably in the exam, the PDEs thing. I wouldn't surprise me. So probably worth making sure you're on top of that. So that constant coefficient and linear means this, that you could have y dashed, something y dashed plus something y equals something. Actually, we're just going to do 0. They're homogeneous as well. I know, and equals some other function of x or t or whatever it is. That's a first order constant coefficient linear ODE, or you could have ay double dash plus by dash plus cy is rx, or ay triple dash. That's the sort of thing we're talking about. I'm putting them all together in one category here. They're all linear, and linear means that the derivatives of y appear only as linear combinations, not multiplied by each other, not squared, and they're constant coefficients. So these things here are constants as opposed to functions of x, where now, it is possible to have differential equations, linear differential equations, which have functions in those spots, but that's not what we're talking about right now. Okay, so the theory of, well, people have been studying differential equations for a while, long before people even had the notation to deal with some of this stuff. And sometimes we have to trust the wisdom of those who have trod this path before us. And the thing that those people know and recognize is that when you have an exponential function, e to the power of something times x, then it will tend to satisfy linear coefficient constant coefficient linear ODEs. And so, well, one of the big vibes of differential equations is saying, this is a kind of solution that I think should be. Let me try and figure out exactly which one it is. That's one of the big ideas in differential equations. You either go, oh, it's an exponential. Oh, it's a power series. Oh, it's x to the power of m. You try things that you think are reasonable expectations for what you think the answer should be like. And that happens, that thread occurs all the way through the differential equation solving methods. And in this one, the thing that we try is this. That is the big thing that this whole thing is based on. And the reason we expect something like that to be a solution is because the derivatives of this function are constants times this function. And therefore, well, that's what this is. This is constants times a function and its derivative. And all of this all of this function's derivatives are constants times this function. And so it feels like the right sort of function to go with this sort of differential equation. That's why. E to the lambda x, lambda e to the lambda x, and lambda squared e to the lambda x, and lambda cubed e to the lambda x. And so on. So every time you differentiate it, that lambda will get multiplied because of the chain rule. And so they are all constant times y, because this is y. That's why. That's why. That's the reason why. Would anyone like to say anything? And when I say that, I mean comment on something I said, ask a question, add something to the list of other things to talk about when I stop talking about this, anything. That's fine, but I need to give you the opportunity. Also gives you a chance to write things down so that I'm not continuing to write ahead of you. Okay, and so when you do that and you sub it in, like this is lambda times y, and this is lambda times y, lambda squared times y, and this is lambda cubed times y, and so on. So that means that if you do try y equals lambda x, then you can sub in a lambda square, a lambda times y here, and a lambda squared times y, and a lambda times y, and then they'll just everything in terms of y, and you'll be able to answer the question. Okay. Oh, crap. The other thing we're going to do is some linear algebra, which is that when you want to solve something, this is a linear operation. If I have two answers for y, then when I add them, there will be a different and new answer for y that will still be a solution. But only if this is 0. I'm just looking at this bit here. If I run a function through here and it produces the answer 0, and I run a different function through here and it also produces the answer 0, then adding them together will be another function that also produces the answer 0. And if I have two functions that both produce Rx, then when I subtract them, when I run it through here, it'll produce 0. And so that's the proof, actually, if you're interested. Suppose y1 and y2 are both solutions to ay double dash plus by dash plus cy equals Rx. So this is a little proof that what I'm about to do is going to work. I'm sorry, I'm not doing it in any particular order. Then that means that ay1 double dash plus by1 dash plus cy1 is Rx. And ay2 double dash and by2 double dash and cy, that's not a y1 dash, that's just a y1. y2 is Rx. And so when I subtract, I get a y1 double dash minus y2 double dash plus b y1 dash minus y2 dash plus c y1 minus y2 is 0. And this, well, this is the same as y1 minus y2 dashed, because derivatives expand. You can do the derivative, add, subtract first or subtract second and then do the derivative. It comes out to the same answer. And this would be y1 minus y2 double dashed. And so what I've got is that, therefore, the function y1 minus y2 is a solution to y double dash, ay double dash plus by plus cy dash plus cy equals 0. So if you have two solutions to the question that you're actually thinking about, which is this one, and you subtract them, you get a solution to the same problem, but with a 0 in that spot instead. And what that means is that if you know all of the solutions to this, then from one of these, you can figure out all the others. Because basically this is saying that if you have, here's y1 and here's y2, I'm drawing them as dots as opposed to functions, then the gap between them is a solution to the homogeneous one. Because y1 minus, sorry, the gap between them. y2 minus y1 is the journey, sorry, y1 minus y2 is the journey from y2 to y1. The gap between them is a solution to the homogeneous equation. So that means that if you add other solutions to the homogeneous equation, you'll get all the other answers to the equation you're trying to think of. That's the proof. That's the idea of the proof. And it's very vector based. I'm drawing them as dots because I'm thinking of them as vectors. So that's the other idea. The other idea that we're going to use is that all solutions to linear homogeneous plus one solution to the same linear but not homogeneous equals all solutions to linear not homogeneous. So that's the word version. The maths version is all solutions to ay double dash plus by dash plus cy equals rx. Sorry, equals 0. That's the homogeneous ones. Plus one solution to ay double dash plus by dash plus cy equals rx equals all solutions to ay double dash plus by dash plus cy equals rx. So your lecturer calls this a particular solution and these two general solutions. But I find those words meaningless. So I prefer to just say all. So those are the two big ideas that go together to solve this problem. And the third big idea is just guess an answer. Right. So I'm not necessarily going to do the guess and answer bit yet for the moment, but I just wanted to get the vibe. So that homogeneous and particular thing comes back a few times in the course. And so the homogeneous general solution to homogeneous particular to original, that comes back a few times in the course. And the guessing an answer and seeing if you've got the right, what number has to go in this spot to be the right answer, that comes back many, many times in the course. I like that I really have properly replaced the Rx with a 0 by drawing a very big 0 over the top of it. It appeals to me. Okay, because the point is that you replace that Rx with a 0 and solve a completely different problem. And then you add those answers to the one answer you think of. Okay, so when I do this, so when I do have, ay double dash plus by dash plus cy equals 0, now I'm going to do the homogeneous equation. and I try y equals e to the lambda x, then what that means is I replace, you know, y dashed is lambda e to the lambda x, which is, yep, that's fine. And y double dashed is lambda squared e to the lambda x. And so I get a times lambda squared e to the lambda x plus b times lambda e to the lambda x plus c e to the lambda x is 0. And so I factorize that out. And I note that e to the lambda x is never 0, no matter what x is. And so therefore this must be 0. And this thing is called the characteristic equation. And it is not a coincidence that we use the word characteristic equation when finding eigenvalues. Because e to the x is an eigenfunction of the linear transformation that is differentiation. When you do the process of differentiation on exponential, you get a multiple of what you had before, which is the same as when you do a matrix on a vector and you get a multiple of what you had before. It really is eigenvalues. So there you go. Okay, so most of the time, this is the proof here, right? Technically, you've got this here as well, but this is the proof that writing this thing is a good idea. But most of the time, when you do the working, you're allowed to just go, the characteristic equation is this, and not put this in, unless you're explicitly asked to explain why it works. How are we feeling? Cool. Right, and so what we do is we solve this, and we'll get some solutions for lambda. And what that means is that if you went back to the beginning and you put those numbers in this spot and you sub them into here, it would come out to 0. And so they really would be solutions. And so it's a quadratic equation, and therefore you expect there to be 2 answers. And those answers may be different. They may be 2 of the same answer, or they may be not even real. But if these numbers here are real, then if the answers are real, then they're going to be complex conjugates of each other. And so that's great. So 3 things happen. Either you get lambda is 2 of different real numbers, and then what you'll have is you'll have e to the alpha x and e to the beta x as 2 solutions. Okay. Or you'll get lambda is 2 of the same real numbers. And you'll get these 2 solutions to the original differential equation, e to the alpha x and x e to the alpha x. And this was your specific question. Why do we do that? Yep, okay. And or you get alpha lambda is equal to 2 imaginary solutions that are complex conjugates. In which case you'll get 2 solutions for the differential equations, which will be e to the alpha x cos of beta x and e to the alpha x sine of beta x. And this is the wisdom of the people who have trod this path before us. I'm being very careful about the way I say this because there is yet another rule that we're going to apply here. So far we've got the rule that that there are certain situations where trying a particular kind of solution, particular is the wrong word, but a specific kind of solution will be a productive approach. And then there is the rule that if I can find the solutions to the homogeneous equation, then I can add them to any one solution to the original, and that should produce all the rest of the solutions to the original. That's rule number 2. And the other rule is, I'm not using that rule here, but the other rule is that if you have a second order DE that's homogeneous and you find 2 solutions, then all the other solutions will be a linear combination of them because they form a subspace with that basis. And in fact, that rule comes back several times. If you can find a collection of solutions which are guaranteed to cover all the solutions if I do linear combinations, then that'll be the linear combinations. And in general, that works for homogeneous equations. So that's the short version of saying that is that these solutions to homogeneous linear differential equation are a subspace. Which means that once you've, and even better, it's not just that it's a subspace, this is the kicker. If it's a second order DE, it's a 2-dimensional subspace. If it's a third order DE, it's a 3-dimensional subspace. If it's a first order DE, it's a first order 1-dimensional subspace. So if it's an nth order, it needs a basis with n functions. Are a subspace. I need to write slower. If it's an nth order ODE, it needs n basis functions. So what I've done is for my second order ODE, I have found 2 basis functions for each situation. And so all the other answers will be A of this one plus B of this one, or A of this one plus B of this one, or A of this one plus B of this one, for various choices of A and B. Yep. So e.g., if e to the alpha x and x e to the alpha x are solutions to ay double dash plus by plus cy dash plus cy equals 0, then all solutions are y equals a e to the alpha x plus b e to the alpha x equals. So in my head, I don't remember the answer with the A and the B. I have a step in between. This is the 2 solutions, and then the answer is made by A of that one plus B of that one. Yeah. And this comes back several times in the course, except sometimes it's like, these are the infinitely many solutions, and it'll be A0 of this one plus A1 of this one plus A2 of this one plus A3 of this one forever. But it's the same idea. It's just that functions are infinite dimensional. Yeah, but a second order ODE has 2 functions needed. A third order ODE would need 3 functions. And back here, you'd be a combination of these things. If you had 2 of the same one, you'd put both of these. If you had 2 different and a third one that was the same as that one, you'd get e to the alpha x and e to the beta x, e to the beta x. If you had 2 real and 2 imaginary, then you get different solutions. They sort of come in pairs. Each single one that isn't repeated has one of these. Each single one that's repeated If it was repeated 3 times, you'd have e to the alpha x and x e to the alpha x and x squared e to the alpha x. Yeah, so that's the story. Okay. Thoughts or questions about that at the moment? Yep. I'm going to repeat that question to make sure I've got it right. And then I'm going to defer it for just a few minutes. So remind me if I don't answer it. So how do you know what style of particular solution to try? Yep. Okay. And I like the word style. That's a good word. I'm sure the official maths word is form. What form? But style is better. In my head. If you're in the Maths Learning Centre, you'll hear me talk like that. I'll use friendlier words. But I can switch over to the other codex if I need to. It's called code switching. It's very common in language, and we do it in maths as well. Okay, cool. And that, you're right, this is only half of the solution. Well, I mean, it's, this is either all or nothing of the solution. You've still got to add the particular solution to these to get all the solutions you really want, because these ones don't solve the problem we were trying to solve. These ones solve the problem with a 0 in that spot just here, and we want to solve it with a whatever this is in that spot. Okay, cool. All right. So I find this a really interesting piece of theory, actually, that it has a combination of we expect this to be the right kind of answer. It allows us to find 2 answers, and then we use the theory of linear algebra as applied to differential equations and show that with 2 answers, we can get all the other answers. I just think it's such a really clever problem-solving technique. Okay, so I'm just going to do a little aside and actually answer the original question you asked. Hopefully, I don't know the proof, so I'm going to give it a go. So part of it is the wisdom of those who have trod the path before us to say that what we should do is multiply by x. So let's just see if it works. So suppose A lambda squared plus B lambda plus C equals 0 has a repeated root of lambda is alpha and alpha. Here we go. Proof of the x e to the alpha x. Okay, well that would mean that it's actually that when you factorize this, it produces this. So you factorize out the a, but the rest of it must be lambda minus alpha squared because it's a double root. So at this point, I decide not to care about what B and C are for the moment, but I feel like I might have to. No, I'm going to have to. So I'm going to expand it out. So a lambda squared minus 2 alpha lambda plus alpha squared. I'm going to get annoyed with that, and I'm going to put the a first. That's better. It's the same thing, but I just feel better about it. Okay, so the b is this number, and the c is this number. This is what I'm thinking. Okay. All right. And so what we're going to do is we're going to show that x e to the alpha x really is a solution. Then y dashed would be product rule because I've got two things that both involve an x. So the derivative, well, I'll keep the x and then I'll differentiate this, which is alpha e to the alpha x. And then I'll differentiate the x, which is a 1, and keep the alpha e to the alpha x. And so I'm going to get alpha x plus 1 e to the alpha x. Actually, no, I'm not going to do that. I'm going to leave it as it is. But I might just make it prettier. Okay, and y double dashed would be the derivative of this. So we'll have keep the alpha x, multiply by the derivative of this, which would be multiplying by another alpha. And then I'll differentiate that and keep the e to the alpha x. And then this bit will become alpha e to the alpha x. And so I'm going to get alpha squared x e to the alpha x plus 2 alpha e to the alpha x. And I have a feeling that when I do it again, not that I need to, I'll get an alpha cubed and hopefully a 3 alpha. No, it's not going to be that. Maybe. I just want to know. Three alpha squared. Wow. Okay. Sorry. That's the pattern. So it's n alpha to the n. That's so cool. Anyway, not necessary, but just cool. Okay. So now to tell if this really is a solution, I should sub this into that equation and see what I get. Sub this into, sorry. I've technically, there's this equation right at the beginning. Okay, so we're going to sub this into that equation. So I need to know what y double dash, I've got y double dashed here. So a of y double dash is a alpha squared x e to the a alpha x plus 2a alpha e to the alpha x, and b y dashed is the same as minus 2a alpha y dashed, which is, according to this, minus 2a alpha times this is minus 2a alpha squared x e to the alpha x minus 2a alpha e to the alpha x. Cool. And cy is the same as a alpha squared times y, which is a alpha squared x e to the alpha x. And when I add all these together, it's supposed to be 0. Cool. So I see an x e to the alpha x here, and an x e to the alpha x here, and an x e to the alpha x here. I see an a alpha squared, and an a alpha squared, and a alpha squared. In fact, I have 2 of them here and minus 2 of them here. So when I add them all together, I will get 0. And the rest of it is this stuff. Oh, and they cancel as well. Yay. And therefore, y equals x e to the alpha x is a solution. Magic. I don't know if there's a better proof than that, but it totally proves it. I enjoyed that. What was the key move that made this whole thing work? Sorry? Well, I mean, getting this, but what was the key move that made this proof work? I knew that it was going to work because it had this. This move here. Writing all the coefficients in terms of alpha was what did the trick. so that when I subbed it in, it really did cancel out. Right. Okay. There is another thing that is in this course that teaches you why there should be an X there. And it is called variation of parameters. No, it's not. It's called reduction of order. And so reduction of order is a process that answers the question that this has a problem of. So when I go back to here, whoops, sorry. When I go back to here, I know if I've got two different answers, then I can go A of this plus B of this, and it gives me all the rest. But in this one, I only really get one answer by copying this same move. So when I go all the way back to the beginning and go, I'm going to try e to the lambda x, that only gives me one thing. And so I have a problem where I only have one solution. And if I want to do the A plus B, I'm going to need two solutions. And so the problem is, if I have a solution to the homogeneous, how do I find one other solution to the homogeneous if I don't have any other way of finding it? And that's what reduction of order does. It helps you find a second solution to the homogeneous equation. Did you want me to talk about reduction of order? Okay, before I do that, I'm going to answer your question. Okay. I don't have to answer them all in the right order, and that's one of the problems with DEs. Everything you do is connected to everything else. And so a nice big mind map with arrows saying how things are connected may help some people to make sense of a course like this. For some people, it will just make it worse. But if you think spatially like that, it can help. Are you allowed to take notes into your exam? One double-sided? Yeah. Now, a mind map like that is probably not useful for a cheat sheet, but it is useful in your understanding of how the course is structured. Okay. Cool. Right. Just going to stop for a moment. Sharpen my pencil. Okay. So, recap. Where have we been? So, recap, where have we been? We've got linear constant coefficient ODE. And it goes, it doesn't matter how many there are, you use a similar process, you just have more solutions to the homogeneous, to the characteristic equation, but I'm going to do second order. What had an Rx in this spot here. And then what we did is we actually solved this other completely different, well, not completely, partially different ODE, and we made a homogeneous linear constant coefficient ODE. And the way that we solved that is we did a characteristic equation. Which gave us solutions, which gave us two solutions, which gave us all the solutions. Something like that. These boxes are not the same things, well, these two are the same as those two. These two are numbers. And depending on what numbers are here, it made you a different choice for these. So that's two solutions, all solutions. Okay. Cool. But there's another part. The problem is, oh, damn it, we haven't solved this problem at all. We've solved this problem. And so that's not helpful. We want to solve this problem. And so we're going to have to find one solution to this. Only one will do. And then if I add all of these to that, it will get to all the other solutions. Okay, so we want to get one solution to the original, and that's where we're up to. We're trying to do that bit here. And this is solved by, there's a word for it, undetermined coefficients. That's what it's called. Because every differential equation solving method must have at least 5 syllables. Sorry, I don't know, that's not a rule, but it seems to be the case. Undetermined coefficients. See, it's got 8, that's great. Okay. So we're going to go back to the vibe, which is guess something that we think might work and figure out the numbers that go with it. And your question earlier was, how do you guess the right thing? So it's not a wild guess. It's a very tame guess. It's an estimate. I'm still going to call it a guess. But it's not an uninformed guess. And it is based on A, following the wisdom of those who have trod this path before us, and B, thinking about what the derivatives of Rx are. Yeah, okay. So you want to try y equals something like Rx and all its derivatives. Something like Rx and all its derivatives. Okay. So let's just think about this for a second. So you'll try that, just saying before we do that, we try that with unknown coefficients, right? And then you'll sub into the ODE and figure out what the coefficients have to be. Okay, that's the plan. That is the plan. The plan. Okay. It's a good plan. I know it starts with the word guess, but you know, that's the vibe of DEs. So now I'll do an example. I'm not going to do a proper example. I'm just going to put, no, let's do it. Yep, I'm just going to commit. Here's my ODE. Do you want me to tell you what some of the words are? So sub into ODE and figure out what coefficients have to be. But it just says coefs. Oh, yes. I hadn't noticed that it wasn't on, so thank you. Yay! And the light is still fine here, okay. I'm in the mood lighting. All good, not offended. Totally fine. Yeah, I warned you about the Friday afternoon effect. Okay. And I'm not going to be 0. It's not going to be 0. It's going to be x sine x. Because. Oh, wow. Cool. Okay. All right. So what I'm going to try is this and all its derivatives. So when I differentiate x sine x, I'm going to get sine x. I'll differentiate the x and keep the sine x. And I'm going to keep the x and differentiate the sine x, and that's going to give me x cos x. And if I differentiate that, I'm going to get differentiate the x and keep the cos x, and so I'll get a cos x. And then I'll get x minus sine x, which is this again. And then I will have covered everything that could possibly happen when I do all the derivatives of this function, as many derivatives as I need. So these are the pieces I'm going to use. That's how I decide. Yep. What if the derivative space is infinite? This approach is not going to work. You would do an infinite series. And if you had to do an infinite series, you would probably use a series method to solve this anyway. Like you would replace this with its Taylor series and make y a Taylor series, and you'd match them up. So in an exam situation, they wouldn't give you one that can't be answered this way, unless they told you to answer it a different way. They'd probably tell you to use their method. Like a clue would be if they didn't tell you to use a series method, then that would you be using the other methods that you know. Yeah. But I'm not sure. The people who run the maths courses are in general very nice people, and they understand that exams are not nice situations, and so they try to make them nice. So they usually do tell you what to do. Yeah. Yep. Yep. I did use a product rule. It produced this. And then I also derived this, and it produced this and that. And I was back to the beginning. Yeah. Yeah. So would anyone like to hazard a guess why I have included all of the derivatives of the original function? Yep. It is just because the derivatives appear in the ODE. I need them to be all there, because if I just included this, these would be here anyway because of this. And so I need to include them just in case, because I might need to cancel out the ones that appear because of the derivative. That's why. Why don't we try it? That was the product rule. Yep. So 3y double dashed. Oh, so that's actually 2a of cos x, right? So 3y double dashed is 6a cos x minus 3ax sin x. And 5y dashed is 5a sin x plus 5ax cos x. And 2y is 2ax sin x. When I add this all together, it's supposed to produce x sin x. Yep. And so let me just, so I've got minus x sin x there. So I've got 6a cos x plus 5a sin x plus 5ax cos x minus ax sin x. And it's supposed to be equal to x sin x, right? This thing here doesn't have an x cos x, so the a would have to be 0. But if the a is 0, then the whole function is 0, and the whole function being 0 is not going to produce x sin x when I run it through here. That's why. But if I had included all of those other bits, then I would have had extra coefficients for the bits that are supposed to be 0 that will not make the whole thing 0. Yeah. So this was a bad move. I do not want to do this problem because I'm going to have to differentiate this twice and sub it in, and I don't want to do it. Is it okay not to do it? I will do it if you want me to. No? Okay. So what I would actually, so this was, don't do that. But this is what I would have had to do, but with also this bit and this bit and this bit. And they would all have to be here, and they together would have to be x sin x. And I would be able to match up coefficients. I'd be able to say that the cos x over here would have to match with the cos x over here. I think you have to be slightly careful about like Ronxian crap, but it should be okay. Yeah, you need them to be independent to be able to do the matching coefficients trick. But you can always do sub in values of x as well. But yeah, even if I subbed in values of x, if I sub in x equals 0, I get 6a is 0, and therefore a is 0. But if I subbed in x equals pi, I would get, no, that'd be okay. No, I would get a not being 0. No, it would still be 0. That's okay. If I sub in a different number, I would get a not being 0, and that would be bad. So I don't get a solution for a. Yeah, if I sub in like a equals pi on 4, x equals pi on 4, then I'll get all these things that aren't 0 times a equals not 0, and so a can't be 0. And so I get two different answers for a, and therefore it's not possible. Cool. So I'll do the same one. With the x to the 5, I'll go, well, I'll try y equals 4x to the 5 and its derivative, which is 4x to the power of 4, but it doesn't matter about the constant because I'm going to multiply it by a constant anyway. And the derivative of that is, 5x to the power of 4 is 4x cubed, but I'm going to multiply it by a constant anyway, so don't really worry about the 4 and the x squared and the x and the 1, and the last derivative of that is 0, so that's going to be fine. So that's why when you have a power, you have to include everything below. So if I had other x to the 4s and whatever, they'd be covered by these ones anyway. Yeah. Cool. There you go. And if it was x to the 5 plus sine x, then I'd do the same derivatives of sine x. So I'd do sine and cos, and I'd include them both. Yeah. I only thought of this rule of the thing and all its derivatives like this year. And it was a unifying principle that made it easier for me to not have to worry about all their rules. I could just do that and it worked. Yeah. All right, and once you've got an answer, then it's the answer. And so I'm going to do one final example for this one. And just do x, if that's okay. No, I won't. No, let's do yeah. Let's do this. Let's do the whole shebang. I'll do it. I'm going to put a number there just to be jaunty. So the homogeneous and the characteristic equation and if you really wanted, you could attempt to factorize that directly, or you could use the quadratic formula, whatever floats your boat. I don't like ones that have a not one there. There's a trick about multiplying these two together and stuff, but I'll just do the quadratic formula. Minus b plus or minus b squared minus 4 times a times c over 2a minus 5 plus or minus 25, 12 times 2, 24, 25 minus 24, nice. And I will have you know, I didn't actually set it up that way. It just happened after I put the coefficients down. I was just trying to make sure that the solutions were real. Yeah, I was just trying to make sure the solutions were real and not imaginary because I wanted to put a sign in. And so I've got minus 5 plus or minus 1 on 6, which is minus 5 minus 1 on 6. So minus 6 on 6 or minus 5 plus minus 4 on 6. And so the lambda is therefore minus 1 or minus 2/3. Okay, cool. So that, and so I got two solutions, e to the minus x and e to the minus 2/3 of x, and therefore all solutions, or if you like, sorry, the general solution, y is a e to the minus x plus b e to the minus 2/3 of x. Okay. Are you ready? I'm going to change the question. No, I'm just going to do the question as is. So now I'm going to try y equals something as a solution to the original. Okay, so my original has a 4x here. I'm going to need that function, and I'm going to change its constant anyway, so I don't need the 4, and its derivative, which would be 1, and so I'll have ax plus b. And so y dashed is a, and y double dashed is 0. And so I've got that 3y double dashed is 0, and 5 y dashed is 5a, and 2y is 2ax plus 2b. And so I've got that this is 2ax plus 5a plus 2b, and it's supposed to be 4x. So therefore 2a must be 4, and 5a plus 2b must be 0 because they match up to the coefficients. And so I get a is 2, which causes 10a, so which causes 10 plus 2b. So 2b is minus 10 and b is minus 5. And therefore, my ax plus b, in order to be a solution, has to be 2x minus 5. Is a solution to the original. A particular solution, because it's not just a random solution. It doesn't have unknowns. I know exactly which solution it is. And so therefore all the solutions are this. To the original equation, y is particular solution plus all the solutions to the homogeneous one. Ta-da! That's the whole process. I do want to ask a what if. What if it had been 3y double dash plus 5y dash plus 2y equals 7e to the minus x? What would have happened? Why would I need to multiply by x? Yeah, okay, cool. So if I did try this, the function and all of its derivatives are multiples of this. And so I would just try this. But this here is already part of the homogeneous solution. It's one of the solutions to the homogeneous equation, which means that if I run this function through this bit, it'll come out to 0. And it will never come out to 7e to the minus x. And so I'm going to have to put something here that won't come out to 0 when I run it through this. And so we actually put an extra x in for the exact same reason that we put an extra x in the other one. When we did the second homogeneous solution thing. Yeah. And so that is why, because in a technical sense, the two parts of the solution are separate to each other. You figure out the homogeneous solutions to the homogeneous equation, you figure out a particular solution to the original. They're separate bits of working, and then you combine them at the end. So there's no particular reason why you have to do the homogeneous bit first, except that if you get something that's in the homogeneous solution as your Rx, you're going to have to check what the homogeneous solution was. So you do have to do the homogeneous bit first, because you can't do the other bit without checking what the homogeneous solution was. Yeah. All right. Variation of parameters. I said I'd talk about that. Oh no, I've mixed up my pages. Just a moment. I really should be numbering them. that, 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 that. We've got that was my summary before I started this thing here. Yep. And then this was the beginning of the constant ODEs. This is this. Thank you for bearing with me here. That's there. That's this. Okay. Because I decided to ignore what IT tells me and put the notes online. Because in 2020, 2019 possibly, they removed all of the notes from all of the revision seminars from the website, and I lost them. So I'm putting the new ones back. Yeah, don't get me started. Some of them, but they're really old ones, no, because I had run out of storage space. So yeah, anyway. And it's a huge project to go and find the old ones. So I'm at least putting the new ones up. Okay. Variation parameters is designed to solve the problem of I only have one solution to my second order ODE, homogeneous. Not variation of parameters, sorry, reduction of order. Oh no, I only have one solution to my second order homogeneous ODE. What do I do? That's the solution. The reduction of order is a solution to that. And so what you do is you say, all right, I have a solution. I'm not sure if it's supposed to be a linear constant coefficient one or not. I'd have to look it up. I think it's linear. Doesn't have to be constant coefficient though, I don't think. Just straight up linear, but doesn't have to be constant coefficient. But it will work for the constant coefficient ones, but it works for all of them. Okay. All right, just a second. I'm just gonna, and it has to be homogeneous. Traditionally, we don't put one here because we divide everything by that and put it in standard form. I believe that's the thing. So actually not that. And normally you call this one P, don't you? Like that. Cool. And Y1 is a solution, but we don't have another solution. So this problem came up even when we had constant coefficients, which is ostensibly easier. And what we did there is we multiplied by X. And so that approach worked. Multiplying the solution we had by some function of X helped. And so here we go. It's the vibe. Try Y equals, do we know what to call it U? Some function of X times the solution we already have. Where U of X is an unknown function. So if we do this with a linear ODE, linear constant coefficient ODE, in the situation where the existing solution is already e to the alpha x, then it turns out that the right function for u is either e to the something else x or x, depending on what the equation is like. Sorry? Oh, it doesn't always work. We have to add some extra things to assume so that it's possible to find an answer. So, I don't know if it always works, but it works sometimes. It works because it works. I don't know why. I mean, it works because when you do it, you get an answer. That's very differential equations thing, right? Why does it work? Because look, I did it and it worked. It seems like a not unreasonable thing to do because it worked before when we're doing linear constant coefficients. So let's just hope. Okay, so y is equal to u times y1. Y dashed is u dash times y1 plus u times y1 dashed because of the product rule. And y double dashed is u dashed dash times y1 plus u dashed y1 dashed. That's the derivative of this bit plus u dashed y1 dash dash plus u, no, I just differentiated them both, didn't I? Differentiate the first one, keep the second one, keep the first one, differentiate the second one. Cool. And so when I sub it into my equation, y double dashed is this. And p of y dashed is this. And q of y is this. And we get that. Ready? Nothing up my sleeve. This bit, they've all got a u. And if I factorize it out, I get y1 double dashed, py1 dashed, and qy1. And y1 was a solution to the original differential equation, which was y double dash plus py dash plus qy. And that, therefore, is 0. So that's good. This bit's 0. Nice. That's why it works. And this bit, not so good. Not feeling good about this. I don't have enough information from here to figure out what u is. There's a constraint we have to add to make it work. Does anyone remember what it is? Depending on the whims of your lecturer, you don't necessarily have to go through this entire proof and you can skip straight to the end. And have I done all my maths right? Just checking. Yep. Ah, cool. Oh yeah, look at that. This has only got u dashed and u double dashed and it doesn't have u in it. And so if I made v equal u dashed, this would only be a first order differential equation and I have reduced the order. Cool, that's why it's called reduction of order. Fun, okay. I still think we need an extra piece of information. And this is supposed to be 0, right? Because my y is supposed to be a solution to the equation as well. Oh, it's so nice. Can I just stop and admire for myself how lining it up this way made it so easy to see that that thing was there? So just thank you. I'm a big fan of lining things up carefully when you do your working. In the notes, there's just stuff flying everywhere. Doing it vertically like this made it easier for me to see those pieces all connecting together. So I've got v dashed y1 and this is now a first order differential equation that is, I reckon, separable actually, because y1 isn't unknown actually, it's a function of x. And so I should be able to rearrange this. This is separable. Yeah. Cool. Sorry? Because this is a 0 here, I don't have to, but I can use an integrating factor. I would have to divide by the y1 to do that. But I can actually say v dashed like dv on dx. And then I could put the 1 over v over here and the dx over there. Integrating factor would probably be ever so slightly quicker, actually. So integrating factor would be, you'd have to put it in standard form, which is that this may not match what's in your lecture notes because I'm just making it up. And so that's in standard form. And so you'd have to do the integral of that, whatever that is. Shall I give I equals e to the integral of all of that stuff? And then you'd go that I v dashed plus I times all of that crap v equals 0. And then that's magically set up so that this is the derivative of that. And so this comes from the product rule. And so you get IV is a constant. Because you integrate both sides. And so V is whatever C divided by I is. And if you're very lucky, this thing here will be like a constant, and you'll get, so you're going to get an e to the power of minus something, right? Because the I is e to the power of plus something. And then you're going to have to integrate that again to figure out what u is. Don't we get two unknowns now? Oh, but they'll all be answers, so I don't have to worry about what the C's are. Oh, that's so cool. Oh, yay. Okay. Is that how it went? I remember doing a Wronxian. And that's not what this did. That's variation of parameters. Yes, that's right. Cool, 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 cool. I get it. I get them mixed up. Cool. So in my arrangement of the way these things work, the second order ODEs, reduction of order was a way of trying to solve one of the problems that came up while you were trying to solve second order ODEs. And variation of parameters is also a way of solving one of the problems that comes up when you do second order ODEs. It's the problem that you mentioned already. You said, what if when I try to do my my undetermined coefficients, I just get more and more and more derivatives that just keep getting worse and worse and worse? Then it's not going to work. And what do you do instead? Variation of parameters is a way of figuring out a particular solution for your ODE from the homogeneous solutions. Yeah. So I'm just going to write that down. I'm not going to necessarily do the whole thing, but that's what it is. So I'm actually going to do exactly the same thing I did here. Oh no. Undetermined coefficients. Is just a world of pain for this Rx. What do I do? Replace it with slightly less pain. And so we're going to say that we have this thing. But it doesn't just apply to the constant coefficient ones, but the constant coefficient ones is one of the places where the problem happens. So we have this thing, and we go and we have two solutions to the homogeneous equation. And they are called y1 and y2. So when we want to get all the homogeneous solutions, we'll go A times this plus B times this. And those A and B are constants. But instead of, oh no, not this one, it's an Rx here. Instead of this one, so we do the homogeneous one, and we get these two solutions, and we can make all the other solutions with the A's and the B's, and that's great. But we need a particular solution to finish off our problem, and we don't have a particular solution. So for a particular solution, we're going to try y equals u of x times y1 plus v of x times y2. Do you call them u and v in this story? Yeah? Wouldn't it be nicer if it was called U1 and U2 so that you knew which one went with which one? I know they're in alphabetical order. That's probably the best plan. Where these are unknown functions. So when you make the homogeneous solution, you put unknown letters there, and an unknown letter is a parameter. And so we are varying the parameters, but they're not being numbers this time, they're being functions. And then we'll do exactly what we did before. We'll differentiate them, we'll sub them in, and different bits of it are going to cancel out because these two are both solutions to the homogeneous equation. But we're not going to have, because there's two unknowns here, we're not going to have enough information to figure out the solution. And so we're going to have an extra piece of information to help us. And I believe, do you want me to do that proofy bit, or are you okay to just skip it? People don't care. All right. I can't remember what it is. I think it's u dashed y1 plus v dashed y2 is equal to 0 is the extra piece of information we need to finish off the solution. So you'll do this and you'll end up with, I think you end up with u y1 dashed plus v y2 dashed. And no, you end up with this. Like you sub in if someone's looking at it, check if I'm right, but I'm like, you sub in to the DE and you do all this working and bits cancel out and you end up with what? I believe it's you end up with something. I could Google it. Just give me a second. Oh, it doesn't even need to be homogeneous. Oh, no, it does. Yep. You end up with, so the assumption is U1, U dashed times Y1 plus U V dashed times Y2 is 0. So we don't get that. We end up with U dashed Y1 dashed plus V dashed Y2 dashed equals stuff. Can't remember what the stuff is. I believe it's probably, oh, it's R of X. Oh, it's so cool. Yeah, it's R of X. And all right, what's the other thing we need to assume? All right, so we get this. U dash, you sub into the ODE, bits cancel out, and you get this. You end up with that. And that's not enough information to figure out what U and V are, even if I call U dash like something else and V dash something else, not information. And so we're going to assume extra that this is also true. Also assume this, out of nowhere, just because. And this is now two equations in two unknowns, because I know what Y1 and Y2 are at the beginning of this entire process. And so I have, and I know what R is at the beginning of this process. And so I have two equations and two unknowns where the unknowns are functions, and it should be possible to figure them out by matrix methods. This is one of, yeah. And so what we have is this, we have Y1 plus Y1, I'll use this as the first row of my matrix, Y1 and Y2 times U dashed and V dashed, and Y1 dashed and Y2 dashed times U dashed and V dashed. And so the first row is 0 and the second row is R of X. And this is now, and look, oh, the determinant of that is the Wronxian. Yep. I'm sure there is a way of doing it for third order, but you would probably get this same thing. You'll get U dash Y1 dash plus V dash Y2 dash plus thing dash Y3 dashed. When the particular solution gives you infinitely many derivatives. Yeah. And plus this also works for non-constant coefficient. So that guessing a particular solution one doesn't work when it's not a constant coefficient, where you've got functions next to the y dashes and stuff. So me guessing the solution was only when there were numbers next to the y dashes and the y double dashes. But if there's functions in those spots, you can't just guess. Yeah. All right. And then that means that if we got the inverse of this matrix and multiplied it here, it would do the trick. And it would tell you what u dash and v dash were, and then you'd have to integrate them to figure out what u and v were, and then you'd have to sub them in to the equation originally that with the u's and the y's and the y2's, and that would tell you what finally the particular solution was. And then you'd add ay1 plus by2 to that, and you get all the solutions. Complicated. Do they do the Ronsian thing here? Did you know the formula for the inverse of a 2x2 matrix at that point when they did it? So when you've got a 2x2 matrix and you invert it, you get 1 over the determinant of the matrix. And you'll have to switch these two and minus those two. And that will be the inverse. And that's why you divide by the Ronsian, because it's the determinant of this matrix. And that's why you need that not to be 0, because you're going to divide by it. Yeah, and so then you multiply this with the y's and y dashes in the appropriate spots by this, and so the 0 means that you don't get anything from the first row, so you only ended up with the second row. And that's good because the second row, yeah, so it's all good. It's very neat. No, I've done it around the wrong way. Sorry, completely wrong. You switch these two and minus these two. Yeah. And so because of that, your u dashed v dashed is going to be 1 on the Ronsian times switch these two and minus these two times 0 and Rx. And so you'll get 1 on W times this vector, which is that times that, and that times that. And so therefore, u dashed is y1 dashed Rx divided by W. It's just such a magic trick, right? And then you integrate them and you get the answers, and then you sub them back and blah, 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 blah. So, yay. Whew. Right. I don't think I can talk about the bifurcation types. I'm really sorry. But I do want to do one last thing. Well, first I'm just going to stop for a few minutes. Well, 30 seconds. Have a drink. Okay. Thoughts, questions? Okay. And go all the way back to here. Not there. Here, homogeneous ones. When you do PDEs, you separate them into 2 homogeneous linear ODEs with constant coefficients. And at the point when you did PDEs, the people who ran your course, and in fact, every possible textbook about differential equations ever, assumed that you remembered everything there is to know about linear constant coefficient ODEs. At this vantage point at the end of the course, we understand how important they were, but you really need to know them. So I'm just going to pause for a moment and go back there for a minute. Second order linear constant coefficient ODEs. Okay, cool. And just some special cases. Here we go. Ready? What if the lambda squared was 0? Then that would mean that lambda would be 0 and 0, and which is a repeated root. And so the two solutions would be e to the 0x and x e to the 0x, right? That's how you do it. And so therefore, which is just 1 and x times 1. And so therefore, all solutions would be something times 1 plus something times x. It's so neat, right? That's special case number 1. Special case number 2. Just going to do it as a specific example, and then we can generalize. Lambda squared minus 9 is 0. That's my characteristic equation. That's giving me lambda squared is 9, which is giving me lambda equals plus or minus 3. And that's two different solutions, right? So two solutions would be e to the 3x and e to the minus 3x. And I would have all solutions, right? Would be a e to the 3x and b e to the minus 3x. Which is fine, right? But not nearly as cool as this. Ready? I know a function that is a combination of e to the 3x and e to the minus 3x. It's cosh of 3x. Cosh of 3x is this plus this divided by 2. So, and sine of 3x is this minus this divided by 2. So instead of using these as my two solutions, I could choose to use these. If I wanted. That's not an E, that's a C. And that's just pretty, right? Like, I mean, sometimes this one will be easier to see what the function's doing as x goes to infinity, but sometimes this one will be nicer. Especially because if I'm gonna have to differentiate this later, differentiating cosh and sine is particularly nice because the derivative of cosh is sine and the derivative of sine is cosh, and the 3 will come out, but that's fine. I just wanted to show it to you. I know that it happens in a couple of the examples and solutions and stuff that just says, what if the solutions were cosh and sine? And someone was in the Maths Learning Centre actually yesterday saying, where did this cosh and sine come from? That's where they came from. So that's another special case. And you can imagine if it's a mu squared. Yay. And then the other special case is this. I'm just going to do it with a specific number. So you get lambda squared is -9. And so lambda is plus or minus 3i. Because the 9 square roots to become a 3, the -1 square roots to become an I. And that's 0 plus 3i, right? And so what you'd do is you'd go, the two solutions are e to the 0x cos of 3x and e to the 0x sine of 3x. But e to the 0 is just 1, and so we just get cos of 3x and sine of 3x. And so all solutions so these are three special cases of the other, even more special cases of the other special cases from the second order coefficient one. And these are not just special because they have particularly neat and nice answers, but because these are the specific ones that come up when you do the Sturm-Liouville problem. Yeah. I don't know if your lecturer talked this through at any point in any of the videos or text, but I love it so much. It's just cute. Yeah, especially the Kosh and Shine. I love it. I will also tell you that I also love this being A and B and not the other way around. Because there's an alternative way of solving this, which is to go, well, if the lambda squared was 0, then that means the original differential equation was actually y double dashed is 0, and you can integrate it twice and you'll get a linear function. That's the other way of doing it. But if you do that linear function, you'll end up with like ax plus b, usually. And I really much prefer the a plus bx because, are you ready? In all of these solutions, my even function goes with a. And in all of these solutions, my odd function goes with b. And that just appeals to me. And it is actually not just appealing, but really important. If you're going to do Fourier series, you either get all even functions or all odd functions when you do this process. And so I much prefer to have the letters match up. But that's just me. So anyway, that's enough of that. It's probably time to stop now. No, but Kosh of 3x is. Well, I didn't do that. Yeah, I didn't do that there. And in fact, if I was going to have a function that was neither odd or even, I would have probably avoid using a and b if I was thinking clearly, just to stop. But so you're right. Very important point. This tends to work on the side of the PDE that causes the Sturm-Liouville problem, which is just f, f double dashed equals kf. The other side, it's probably a good idea to keep your e to the power ofs, because that's the side with the Sturm-Liouville is the bit that causes the oscillating bit, and the other side is the bit that causes the decaying bit. So you normally leave the other side with the e to the power ofs. Yeah. Cool. Thank you. You're a good crowd. I'm just going to stop the recording.